Right. So last time in the latter part of the lecture, I looked at this notion of a pseudo divisor. Associated to which we had the notion of its support, which once I write it like this is just another notation for this same Z. And we had an operation which was intersection with the pseudo divisor, which from what we did last time, so I'll write it like this. This is a map from Zm x to tau m minus 1 of d. There was such an operation which we constructed. And we reviewed various properties of this operation. That's what we kind of did last time. So let's carry on with that for some more time. One of the key things is something called commutativity of intersections. This is a very important property. There are various ways of formulating it, but let me write something which works for me. Let D and D prime be Cartier divisors on an integral scheme X. Then, if I look at D dot D prime dot alpha, that's the same as D prime dot D dot alpha in Chow. So m minus 2, I should have said what m is, for all alpha in Zmx. So I should have written it perhaps the other order. Start with the cycle alpha in dimension m, take two Cartier divisors, interact with them each Cartier divisor on an integral scheme gives me naturally a pseudo divisor. And if I have any subscheme of a scheme where I have a pseudo divisor, I can restrict it to the subscheme to get a pseudo divisor on that subscheme. So whatever this object is here in the middle, it makes sense to intersect D with that in the sense of pseudo divisors. The operation is D is a Cartier divisor on X. So therefore D is a pseudo divisor on X in a tautological way, but then anything mapping to X I can pull back and get a pseudo divisor on that thing. And then intersection with the pseudo divisor makes sense on that in that place. Okay, so alpha in Zmx, a cycle. Well, I mean, when you make a statement like this, you're really saying take alpha to be an irreducible subvariety of dimension m and write the thing, but then, I mean, we might as well formulate it like this. No, D prime dot alpha will make sense in the Chow group of D, of the support. But because of the nature of the dimension, I suppose it will be clear that if alpha was the class of an integral variety, that corresponding Chow group is the group of cycles. It will be in the maximal dimension automatically. Somehow has to be, that's how it will work. So in particular, therefore in particular I can say D prime dot D dot the class of X itself, which is really the key. I mean, when you write a statement like that, you're really proving this is equal to D dot D prime dot X. And also, what is this D dot X? This is just the class of the veiled. So this is D is a Cartier divisor. This is another notation for the Weyl divisor associated to D. Because again, look at the dimensions. So what we earlier said, take the underlying Weyl divisor. I can view it in this fancy language as taking dot with the class of X itself. I mean, if I choose, I can do that. So the assertion is that you have this commutativity property. This is the fundamental thing which constructs whatever intersection theory one does in the end to show that you get a commutative ring. This is the thing which lies behind that. Right? So this is a very fundamentally important property of the intersection theory, that this thing is true. Proof is not so simple. This is one of the difficult early proofs in Fulton's book. I think maybe Nitin's lectures covered this. You did this? Yeah, okay. So it's induction with some blow-ups and so on and so forth. So it's a tough argument. But what's the key idea behind it? It's a fairly straightforward idea in good cases. And then the problem is the general case is not good necessarily. And how to reduce a good case gives you a lot of difficulty and so on. I see. In any case, I want to just make some comments without, I'm running over all the steps, but being very sketchy about the details, saying this is the types of things which went into it, this is the way you think about it, and details have been given. Okay. So let's, the sort of basic case, or most important case, is when D prime are effective Cartier divisors on X which meet properly. In other words, if I take the support of D, intersection the support of D prime contained in X has pure codimension 2. And this is the best possible situation. And then the problem is the general case, it's not true. And if it's not true, by what extent is it not true? Can I measure that? Can I lower that by blow up, etc., etc.? Those kinds of things. But let's take this best possible case. So suppose you had such a W, a component of that intersection. Then I can write the local ring of the generic point of W on X. This is a two-dimensional integral local ring. Yeah? XW? Whatever. It depends on the pair. Which way you order it is a matter of your convention. Really. I've forgotten what is the standard. Okay. OX. But don't people write this for the local ring at X? Some people do, right? And little x could have been the generic point of W. Anyway, doesn't matter. We all understand what it means. In the scheme sense, there's a generic point of such as W. It's a codimension 2 point inside the scheme X. So the local ring of that generic point is a two-dimensional integral local ring. And then I have the ideal of D and the ideal of D prime, because D prime are effective, and they're both sitting inside this. And because they're Cartier divisors, this is the principal ideal A and this is the principal ideal B. So if I'm looking at this situation, I'm saying these two things are equal as cycles. That's the assertion basically. In the cycles of dimension m minus 2. Right? So I have to check therefore that each W which possibly appears in that intersection comes with the same coefficient on the two sides. So I want to know that those coefficients are equal. That's what we have to check. So there are two multiplicities associated to W by the two sides of the equation. I have to check, are they equal? So how do I understand what those multiplicities are? The first thing is I take A mod AA, or let me say A mod BA, and take multiplication by A and take A mod BA. This is a complex of finitely generated A modules, if you like, and the homology, there could be a zeroth, or zeroth and minus, if I write homology, zeroth and first homology. If I write cohomology, I suppose I should think zeroth and first, depending on which way you want to write it. So I suppose for algebra, I have to think of this as in degree 0 and this as in degree minus 1 if I think cohomologically. Okay? If I think of this chain complex, there's a certain quotient here. What am I also given? I'm given that W is an irreducible component, which means that if I call A this ring, then A mod AB, the length is finite. Right? That's what you mean by saying W is an irreducible component of the intersection. And then associated to that finite length thing, I can write, for example, this complex. So this has finite length. And the kernel also will be finite length. So I can make sense of an Euler characteristic over A of this complex. This makes sense. This is some interior. The length of this minus length of that. So I claim this Euler characteristic is in fact just the coefficient of W in D dot D prime dot X. I'll leave you to think about why that's the case, but there's a particular order in which we've done it. We've done D prime inside. So we replaced X by D prime basically, and then try to do an intersection. What is D prime? It's spec of A mod BA. So on the scheme D prime, which is now perhaps a bad scheme, I have still the Cartesian or pseudo divisor corresponding to the principal ideal A, and I'm trying to intersect with that. And now multiplication by A may be a zero divisor, so there may even be a kernel. Doesn't matter. Chi makes sense. And this would be the Tor or whatever it is, if you like. So this would be the formula. And the other intersection is a very similar thing, but we're interchanging the role of A and B. So the other one, similarly, chi A of A mod AA, A mod BA, sorry, A equals coefficient W in the other intersection, D prime dot D whatever. Sorry. Huh? What's that?
When you are writing D times square bracket X, that is the square bracket.
Yes, it is. Which is why I was able to reduce it to this complex. I mean, so to speak, this is square bracket D prime. This object here, spec of that, or it's not quite, but it's the generic. I mean, it's some suitable germ of an object related to that. So the question is, why are these two Euler characteristics equal? That would be finally the question. And both of them are equal to the Euler characteristic of the causal complex. And here, let me call it F. F goes to, I suppose, minus B E1 plus A E2. Right? This is the causal complex. Of the sequence AB, if you like. Well, ordered sequence AB. And a standard thing about, right, this is the standard causal complex. But I can think of the causal complex as taking two complexes let me be very pedantic then and write it like this, where E1 goes to A. It's just A to A, but which sends the generator to little a, which in other words is A to A multiplication by A. Okay? Tensor 0 to A E2 A to 0, where E2 goes to B. This is just multiplication by B. Standard thing. The causal complex for a sequence of elements is just take one element at a time, take a two-term causal complex, tensor all of them. There's a standard operation of tensor product complexes. It introduces some signs, which is why you got some minus sign somewhere in some formula. You do that. Yeah? Total complex. Exactly. Well, that's if you think of tensor as a double complex. If I think of tensor as an object in the category, it's a complex, and that's the definition. Right. Okay, but notice that, for example, this complex has a map to the single thing which is A mod A in degree 0. So this is degree 0, this is degree minus 1, this is again degree minus 1, this is 0. Right? So this complex is quasi-isomorphic to just a complex which is little A mod A in degree 0 because A was a domain. So little a is a non-zero divisor. So there is no kernel here, there is only a co-kernel, and this is correct. Similarly, this is also quasi-isomorphic to A mod BA. Now let's just use one of these quasi-isomorphisms and keep the other complex in the moment and try to tensor. Of course, tensor of this with this is causal, but tensor of this with the quasi-isomorphic thing is this complex, right? Because this is, I took multiplication by B and this was A to A, but now I tensored with A mod A, so it's multiplication by B on the quotient A mod A. It's the second one? Okay, it's this one. Sorry. Okay, and notice that, of course, this is a complex of free modules. So, quasi-isomorphism is preserved. So then I get the Euler characteristic of this tensor product is equal to the Euler characteristic of that tensor product. And by the same reasoning, it's also equal to the Euler characteristic of that tensor product. That's what we wanted. Okay? So little homological algebra is involved. The place where you interchange them is somehow in this causal complex, there's a place where both of them live together. And then which direction you want to go is somehow up to you. Of course, you order them in some fashion, which one is first, which is second, because of this minus sign. Doesn't matter, it's not so important. Euler characteristic, it doesn't matter for this. For other fancy things, probably you should be keeping track of the sign and the orientation, things like that. Total headache. But anyway.
I did it by snake with my mind.
Right, but I thought this is an insightful way of thinking about it. I thought it's good, people should see things like this. And also it's an argument purely with diagrams. I never computed length of anything. Many arguments in this, there is an underlying algebra at the level of diagrams, which implies the actual calculations which you do directly. That's also something to learn from these kinds of things. When you say intersection theory, maybe you really mean take this complicated diagram, that one, take some tensor, do something, and digest it and get another diagram. That's an intersection computation. You know, you have to think like that sometimes. So that's the sort of thing you try to learn maybe from the course. Okay. Right, so this is this. This takes care of this. Yeah? A module? Complex of A module. Absolutely. Absolutely. No. And as is being commented by various people, there are subtleties about how to take tensors of complexes and signs and things of that kind, which have to be there in some sense, because if you do abstract general things like this, will cover things like what you'd see in topology. You have two spaces x and y, take the complexes which compute homologies of x and y, and the tensor product complex is equivalent to the complex computing homology of x cross y. It's not equal, but equivalent at least by some theorem. But you know, things are not commutative there. You interchange the things as signs. So your theory has to take that into account at the level of complexes. So there are various subtleties one has to pay attention to. Okay. Anyway, one nice corollary of this commutativity thing is the following corollary. If alpha and Rmx for some x and a cycle rationally equivalent to 0, and if I let D be any pseudo divisor, then sorry, not mod D, mod, no, let me write it like that. I claim this is correct. This is the same as chow and minus 1 of the support of this. Exactly, that's the point. I could, you're saying, yeah, probably. But this is good enough for me for the moment. So, to prove it, I might as well assume alpha equals x, where x is integral. No. That I can't assume that. If I could assume that, I'd be okay. I have to work a little bit. If a cycle is rationally equal to 0, the simplest version of that is taking an integral scheme and a function and the divisor of the function. So that's what I have to take. May I assume x integral of dimension m plus 1 f in kx cross a rational function, non-zero rational function, and alpha is just the divisor on x of f, and take the underlying cycle. Rational equivalence is, by definition, generated by cycles of this type on suitable spaces. So this is the basic example. If I can check here it's correct, then other cases will follow. But the point is, I deliberately wrote it like this. I noticed that this square bracket thing which I talked about is a way of thinking about how to associate a Weyl divisor to a Cartier divisor. But the divisor of function is a Cartier divisor to start with, and later I viewed it here as a Weyl divisor, so to speak, losing some information. So I might as well think of this as take the Cartier divisor div x f and take dot x, right? Where this is now Cartier. Now I'm trying to compute d dot this object. D dot whatever is underlying this. This is the object I would like to show is 0 in some Chow group. But according to our commutativity, which we stated and I proved in the easiest case, this is the same as div xf dot d dot x. But now let me just not bother with writing it like this, let me just write it like this. The same thing. But now this is some element in Chow m minus 1 of mod d. Right? The definition. But we know that this is 0 because the line bundle L in question is isomorphic to O of div. The line bundle L is O of div xf. This is a Cartier divisor that has an associated line bundle. But this is isomorphic to OX because it's a principal divisor. And we know that if the line bundle underlying your pseudo divisor was the trivial line bundle, then the class is rationally equivalent. That was proved earlier. So I got what I wanted. Doesn't matter. The homologies are finite. Yes, take the homologies, take the lengths of each of them, take the altering sum of the lengths. That's Euler characteristic. That's the definition. Yeah. Euler characteristic is defined on, so to speak, the class and the derived category with support, so to speak. You want to be fancy about it. I can take that as a definition of Euler characteristic. Yeah. Well, it's a meaningful concept, yeah. Complexes of finitely generated modules with finite length homology. This category comes equipped with a natural Euler characteristic.
I'm saying the tensor product happens when you go outside this. The Euler characteristic happens on this.
Yes, if you want to be very fancy about it, each of the particular elements were in some categories of, so I can take the category of bounded complexes of finite generated modules whose homologies are supported in a given closed set. If I have two such given closed sets, I can take some kind of tensor product and argue the support of the tensor product is in the intersection of the two sets, which is reasonable. I'm intersecting two divisors. I mean, it's a reason. There's a reason why we use the same language to talk about both of the things. It is essentially the same operation. Absolutely. That's the abstract thing. Everything always lives in an ambient space which supports, and all operations, I mean, depending on which ambient space you do, they depend on, right. And things don't depend on the ambient space so much, provided the ambient space is non-singular. Then they really are intrinsic to the support. Otherwise, it does depend on the way in which this singular space is sitting inside that one. And it does, and those things do. But there are in principle operations. Tensor product I can make sense of. If I want to say quasi-isomorphism, I have to argue a little bit, which is why, yeah. In abstract language, you'd say something about this being a perfect complex and this being another kind of complex, and therefore tensor operation is a good operation.
Proof like these man also avoids all this.
No, it will prove the result. It won't explain it.
Exactly. That's why I like this better.
Yeah.
But then I had this.
Okay. So this is kind of important for the theory. This is an example where I have something which is rationally equivalent to 0, and after intersecting, the result is rationally equivalent to 0. This is the kind of thing Anand struggled very hard to prove in the morning. Right? In usual cycle theory, it's a real mess, and we're not even sure we fully understand all the details of proof, or maybe in full generality whether it works. So having this for us here is very good. This is, and if I understand right, in the Fulton context, this is the only case I have to check this directly by some method, which is done by that repeated blow-ups and some induction. After that, somehow you use different formalism and just construct the product directly. That's somehow the way the theory works. That's why you don't have such a nasty moving lemma, like the second hard moving lemma which he attempted to do in the morning. That's not there at all in the Fulton theory directly. Right, so therefore, if D equals L Z S a pseudo divisor on X, and I have F Y to X any map, there exists induced operation chow lower p y to chow lower p minus 1 of support of f upper star d, let me put it like that, given by alpha goes to f upper star d dot alpha. Or I should say class of alpha maybe goes to this. And now it's defined at the level of Chow groups on both sides. This is what I want. So really produce an operation on Chow groups in some fashion. Okay. Now I can abandon some of this pseudo divisor stuff and go in the direction more of Chern classes and cycles and the like. So let's talk now about C1 of an invertible sheaf. Let's just remind you. Oh yes, I should have said something here, that if X is non-singular and I look at chow p x to chow p minus 1 mod d, and then compose with going back to x and look at this operation. I have d on x. Of course, this operation which we constructed here goes like this, but in addition I can forget the support condition and just go back to x. This operation is just take the class of d in chow upper 1 x, or otherwise chow lower dimension x minus 1 x, divisor on x, and just take dot, which is multiplication in the chow ring of x. Since x is non-singular, if x is non-singular, a chow ring has been constructed by the other lecturers, and so I'm just claiming that in the special case where there are two definitions, one is the definition I've given here, and the other is intersection of the class of D, they're the same thing. The way the intersection product was constructed, this was built into the definitions. In fact, the way the intersection product is constructed is somehow you reduce the general intersection problem to multiple use of this intersection case. So, in some sense, I'm logically going around in circles, but all I'm saying is for the purpose of my lectures, whenever I need to say x is non-singular, it's just the ordinary operation which has already been constructed by somebody by some method. Okay? I'll need that because sometimes I need to use the other properties of the chow ring which have been constructed, which I'm certainly not going to treat in my talks. For example, if I take any map x to y of non-singular varieties, there's a map from the chow ring of y to the chow ring of x by pullback. Well, for general cycles, only flat maps have a pullback, right? But for non-singular varieties, the theory of intersection produces a pullback, whatever it is. So I might want to use things like that, and then I want some compatibilities between whatever I did and that theory. So, I mean, the point of view I'm taking is I'm not giving you a systematic theory of intersection completely. I'm doing as much of the intersection theory as I feel is relevant to doing the proof of the Riemann-Roch theorem. Everything, my goal is entirely Riemann-Roch is there, only what is needed for it is being developed in some tunneling fashion. And some few comments here and there which I can try to make, I'm doing, but I'm focused only on the goal, okay? And I'm not thinking about the general aspects, which have been done by other lecturers, so therefore it's okay for me to do that. Anyway, now let me write some properties of this, so I haven't said what is C1. Sorry, this was a thing, I started writing something and I really had forgotten to say that. So what is C1 of an invertible sheaf? So I have L in pick X. Then there's an operation which I'll write like this, C1L cap blank, which now goes from chow Px to chow P minus 1x for all P. Well, P get no 0, I can say this is 0, okay? Because I can choose a representative pseudo divisor if you like for L, and then there'll be an intersection operation which goes into the support, then I forget the subtlety about the support, go back to the space X. That operation always makes sense. I'll call that C1, it's by definition. C1 of a line bundle is the operator which sends each chow group to the next lower one by this intersection operation and then forgetting the support data, okay? And again, this has the property that if X was non-singular, it's a particular case of that operation, which has already been defined. What are properties of this thing? There's some simple properties which follow from whatever we've done so far. Let me just list them, but so that I can. Proposition. X be a scheme. Then L alpha goes to L cap alpha, pick X cross chow Px to chow P minus 1x. Sorry? C1L cup. Absolutely right. I'm just making it completely explicit. If X is non-singular, this is the same operation which you already had. But now I'm extending to arbitrary X, where L is in pick X. And then you have obvious things like L prime in pick X. Then I can do C1L cup C1L prime cup something. That's the same as C1L prime cap C1 L cap plus. This operation is usually referred to as cap, and this one, if I write alpha like this operation is usually called cup, right? This is cap, and then C projection. Obvious things, if Fy to x proper, L in pic x, alpha in chow Py, then F lower star of C1 F upper star L cap alpha is equal to C1 L cap F lower star alpha in chow P minus 1 x. And then similarly flat pullback. F y to x flat of relative dimension d, then alpha and chow px So cap with C1L and then pull it back, increasing the dimension by D, or pull back the invertible sheaf, pull back the cycle and cap it in the other space. It's the same thing. And so these are obvious properties. And proofs are obvious from things which we've already seen. I mean, there will be some cases the proofs are not obvious. I may or may not do them, but I'll at least try to indicate this proof requires work and this proof is obvious. So this is obvious. Everything here is obvious. So using this machine, we can then define Segre classes of vector bundles. So here there's some slightly tricky choices because of, how do I put it, the way the Grothendieck formalism works for projective bundles, and also certain classical choices which were made long ago before there was any Grothendieck or before whatever. That certain things should be positive, certain things should be negative, etc., etc., those kinds of things. So because of that, we'll do things which look a little funny, but it's mathematically rigorous and it will be compatible with whatever was done by the classical geometers. So that's required for this. So let E be locally free of rank little e plus 1. Why have I written some strange number like this for the rank? Because I'm going to take the projective bundle. So the dimension is going to go down by 1 and E will be the relative dimension of that flat morphism. Okay? So then I define phi Pe to x associated projective I'll put it in quotes because this is not what would be associated by Grothendieck. This is associated as in Fulton's book, and the notation I'm using is this P rather than what we would normally use is blackboard bold P. And so let me spell it out completely. So given scheme theoretically by PE is proj on X of the following graded sheaf of algebras. Take the symmetric algebra of OX over OX of the dual locally free sheaf to E. This is the definition. Right? So this is as in Hartshorne's book, I've got a graded sheaf of OX algebras. I can take its proj. Symmetric algebra is an example of a graded sheaf, right? So what are the properties of this thing? So this is the parameter space for one-dimensional vector subspaces in fibers. What are fibers? Things of the form, you take the stock at X, tensor the residue field. This is a vector space over Kx, of some dimension E plus 1. So I have the space of lines in that vector space. So space of one-dimensional vector spaces inside that, which is also isomorphic, of course, to the parameter space of one-dimensional quotients of fibers of the original script E. Of script E dual. To give a one-dimensional subspace of a fiber of E is the same as to give a one-dimensional quotient space of the dual. But the Grothendieck proj construction looks always at one-dimensional quotient vector spaces of a vector space. That's proj of the symmetric algebra. Some of the thing between algebra and geometry, there's a dual involved. And if you've gone through all those Hartshorne exercises, he talks about geometric vector bundle versus locally free sheaf and going back and forth. And there's a dual in the middle. So that dual is showing up here in this fashion for us. Okay. But you have to keep track of various signs. I hope I've got them all correctly. I tried, but it's possible I might have goofed myself. So now notice that there's a sheaf which I'll write like this: OPE of minus 1. This sits inside pi upper star E. This is somehow the universal line subbundle. So how do I think of that? So then, if it's supposed to be the universal line subbundle, there must be a corresponding dual map. As usual, we'll write, once I've got an OP minus 1, some line bundle, the OP plus 1 is the dual line bundle, and then OPM for any M makes sense for tensor powers. If M is negative, then it's a positive tensor power of O minus 1. O minus 1 is this invertible sheaf, take that particular tensor power. On the other hand, if M is positive, it's a positive tensor power of O1, which is the dual of that. So either way, there's that standard there, and this is my notation, right? The usual notation. Let's notice that, how do I say this? This is the same as O in the Grothendieck sense of PE dual of 1. Grothendieck could say, take proj as a symmetric algebra or some locally free sheaf. There is a canonical O1 defined by Grothendieck, and that's a quotient that is the universal quotient of the pullback of the locally free sheaf. So that's what I've done here. I pulled the locally free sheaf E back and found a line bundle quotient. And by asserting that's the universal quotient of the dual, that's the same as saying that other one is the universal sub. Okay? So I believe the conventions are properly followed with this. Okay, just notation so far. What do I want to do with this? So in particular, I can now speak of zeta, which is C1 OP E of 1. This lives in chow upper 1. And of course, we've got this morphism pi. Pi is proper, and also flat of relative dimension E. So I have operations pi lower star as well as pi upper star on cycles. So therefore I have pi lower star chow I PE to chow I X. And I also have pi upper star, which goes from chow JX to chow J plus E of PE. And of course, I've got zeta, so I've got zeta cap something. This operation also makes sense. So I have these three operations I can do on cycles. So combining all of them, we can construct all sorts of things, the so-called Segre classes. Right, this is the definition of Segre class. Pull the cycle alpha back to PE. Now there I have this zeta. I can multiply by zeta any number of times and then push forward. I have some elements. So in fact, this naturally makes sense for all I greater than or equal to minus E, you can say. Even for negative numbers, the operation is meaningful. But now I can write down some properties of this immediately. Si equals 0 if I is negative, and S0 alpha equals alpha. So the zeroth operation is the identity. I mean, it's some complicated geometric operation. I took a cycle below, pulled it up, intersected it E times, where E is the rank of that projective bundle, with the class O1, and then push it back down. I get back whatever I started with. That's what it's saying. B, if E, F are locally free on X, then there's a commutativity associativity formula, SIE cap SJF cap alpha equals SJF cap SIE cap alpha. And then there's projection formula. If Fy to X proper, and E locally free on X, alpha and chow P Y, then SI E cap F lower star alpha, yes, is equal to SIE, is equal to F lower star of SI of F upper star E cap alpha. And then similarly, I have the flat pullback property. If I have y to x is flat of relative dimension d, E locally free on x, then alpha and chow px, let's say, then I can form F upper star of SIE cap alpha, and on the other hand I can form SI of F upper star E on F upper star alpha, and these agree in chow P plus D minus I of 1. And the obvious compatibility. Okay, and then there's a sort of normalization. If E is a line bundle, now this number little e is 0, the projective bundle is the space itself, then S1 of E cap alpha is minus C1E cap alpha. It's important there's a minus sign here in this formula. That's because of various ways. I took dual somewhere, I took subspace rather than quotient space, I did various things. That produces minus sign. And it's important. In the end, I'll write something. I've defined the S's to begin with, but I really want the Chern classes. And they're going to be with some sort of inverses. And those minus signs and this one will kind of get rid of each other, which is what I want. So this sign being minus is very important. Yeah? Yeah. No. Because it says take the projective bundle of E dual in the sense of growth theory. Take the O1 of that thing. That is the line bundle whose C1 is used to define the secondary classes. But no, hold on. I took E dual, but E is a line bundle. So the proj of the symmetric algebra of E dual is the space itself, and the O1 is E dual. It's not E. So the point is S1 is cap product with the Chern class, if you like, of the inverse of the dual line bundle, which is why there are minus sign. So some of the convention is such that I'm forced to put minus here, which is good for me in the end. Chern class will have plus everywhere, which is what I want. Okay, so F, just compatibility, if X non-singular, E vector bundle SIE alpha and chow px, then SIE cap alpha, I can think of it in this fashion. Take SIE cap the class of X itself dot alpha, and this is product in the chow ring. But in a sense, if you remember how, I'm sure this is how the product was constructed in the chow ring, right? You had chow homology classes, chow cohomology classes, so to speak, some contravariant things, and then there was a Poincare duality. This has been done, right? The chow ring has been constructed, right? So what? Or Anand is going to do it, or it's already done? Chow ring has been constructed, the multiplication with all the properties have been proved, right? Or will be proved later. Kind of did it, no, but he's going to do it the other way, the Fulton way. So the way it's done through the Fulton thing, this is the definition of the intersection product. This side is the definition of that product, so to speak. You always take the, in other words, you say cap product with the class of the space itself is a map from cohomology to homology, which is an isomorphism. I mean, that's how you interpret the intersection product. Okay? And it doesn't matter. It's part of the way the intersection product is constructed in the Fulton theory. This formula is built into the definitions. It's important for me. I need to use this actual formula in calculation in various places. It's some tautology looking thing, but it's correct. The way in which the intersection product is constructed in the chow ring, in the non-singular case, you just take the ordinary, the chow homology, direct some chow lower, asides. And what is the multiplication on this thing? I really think of this as chow lower ix, and the multiplication is going to look like this: chow lower jx will go where? What is it? I plus j minus d, is it? Right. This should be chow d minus I. This should be d minus j. If I add these to z, it should be 2d minus I plus j, which is d minus I plus j minus d. Right? So the product is supposed to go like this. But the way it's actually done is, you think of chow ix as chow upper d minus ix. But an element here, if I have some alpha here, I can make sense of alpha cap x. And I think of this as lying in chow lower ix. I think of defining these things directly in some fashion. Okay? In particular, whatever they are, there are some kind of operators on the chow homologies. So in particular, it operates on the class of x itself. So it gives me an element in chow lower ix. This is the isomorphism between this and this. That's how the theory works. Okay? And then you want to construct the product, you just take this same alpha, which you now think of as an operator, and let it operate on the other one. And the commutativity says you can do it in the other order also. Okay? So this is how the multiplication works in the chow ring from the point of view of the Bolton intersection theory. You directly construct certain things which operate on homology, and you call those things cohomologies. And then if x is non-singular, you say those cohomologies are isomorphic to the homologies with some other indexing. And in the nature of things, those cohomologies, those operators, I can compose any two operators. So, but the operators are isomorphic to homologies, so I can take two homology classes and associate another class. I mean, that's the way the operation works. Okay? It's a very indirect construction. Right. So, in particular, I mean, I get a formula like this as a special case. So now let's see why are these things correct. So I claim most of the things are sort of obvious. These two are obvious. This is obvious and this is obvious from just the definition of the cycle properties. Some of the other things require a little discussion. Let's see how to do that. For this, for example, you would expect it to follow from commutativity, but you have to formulate the thing a little carefully. The way you do it is like this. It's a natural thing to do and it works. If you have two vector bundles E and F, then you have two things like this, right? So I can now take the fiber product Q, which is at the same time P of eta upper star E, and is also P of pi upper star F. And I have a map H here. And then you have to make the following calculation. I'll just write down the formula, leave you to check that it's correct. It says that SIE cap SJF cap alpha is the same as H lower star, let me say, is equal to H lower star of C1 OP eta upper star E of 1 to the I cap C1 of OP pi upper star F of 1 to the J cap H upper star alpha. Yeah. So here's this thing uses this projective bundle. This operation uses that one. But of course, if I have this, if I think of this map Q to PF, that's the pullback of this map under some suitable operation. So there's a compatibility between this Segre operation and that one. And similarly, this Segre operation and that one are compatible. So you have to use this compatibility and projection formula and write everything up here. And then I claim you do that, this is the expression you'll get. This inner thing is this product, but thought of from the point of view H. And then I have this outer one here, which is this. But now once I've written it on H, then nothing prevents me from associating and commenting these things. It's clearly the same thing the other way. Right? So that's what you have to check, that this is equal to this. Then this expression is obviously kind of symmetric in some sense. So that's not so difficult, it's this. What we have to discuss a bit about why SI is 0 for I negative. A priori, there could have been some classes. and the 0th class is the identity. I need that. Let's see that. This already I explained why. I said the projective bundle is the space X itself, but the line bundle got dualized. So, and this is just how the Chow ring works. So really this property is the one which we have to check. Well, so I might as well take alpha equal to the class of X, the X integral. Right, I want to say something about the operator applied to alpha. So we reduce to this case. Now, what kind of operation is S minus I? It goes from Chow P X, X integral of dimension P. If alpha is in Chow, I'm thinking of Si as an operation from Chow P X. So a generator here is an irreducible variety of dimension P. So now if I had a negative Si, it will increase the dimension. I mean, if I took S with a negative index, that has to increase the, but X itself has dimension P. So this is just 0. So this is sort of obvious actually. The other one, why is it the identity? Well, I want to check that S0 Chow Px to Chow Px is the identity. But because P is the dimension, this is just Z times the class of X. So S0 of the class of X is what I want to compute, and it's some integer m times the class of X, because both sides are the integers. So the question is computing this coefficient m, whatever it is. But now it's compatible with flat pullback. So replace X by open set. So if you want very pedantic, if I have a U in X open, I'll go Chow Pu to Chow Pu, and this is the flat pullback for the intersection. If J is the inclusion of U in X, I'd have a J upper star here. And I know Segre classes are fine for flat pullback. This formula is true. So whatever this integer m is, I can capture it on any open set. So I can pass to an open set. So may assume E is just OX to the E plus 1. It's the trivial bundle. So I might as well assume that this space PE by PE to X is just X cross projective E space to X projection. And I want to check it in this case. What is the invertible sheaf O1 in this case? So I claim the O1, OPE of 1 is just, so let's call this projection Q, Q upper star OPE of 1. Just take the O1 on projective space and pull it. It's the trivial bundle. So this is clearly correct. So what I'm trying to do is I'm trying to look at C1 of Q upper star OPE of 1 and trying to compute, for example, what is the cap round with X. So what is this? I claim this is just, well, I can write lots of divisors which represent this C1. For example, I can just take X cross a hyperplane, where H is any hyperplane. That's a Cartesian divisor, and this Cartesian divisor represents that line bundle. And I can construct this C1 cap operation using this particular representative. So if I take X cross H and then cap it with X, think about what that is. Cap it with pi upper star X. But pi upper star X is of course just the same as X cross PE, the total space itself. If I pull back the class of the total space under the flat map, I still get the class of the total space, right? So I'm computing this thing, and then I have to do it many times and then push down. That's the definition. S0 is I have to do this operation E times and then take lower star. That is the definition. Right? So I'm trying to do it once first, then I'll try to repeat the process. I claim this is just, if I think about it, just take the class of X class H itself I mean, it's just the way the definitions are. It's just a bunch of notation. It's just a way of writing x cross h. And I could have chosen any h. So if I want to do it the second time, I choose a different hyperplane h prime and then operate. Then I'll intersect h with h prime. And if I want to do it e times, I take e hyperplanes. So doing it e times, I'll be finally left with the cycle which looks like x cross point. And then I'm trying to take pi lower star of this. Of course, this is the class of x. So it's the identity in this case. This was after passing to that open set. So even on a general x, the integer m has to be 1. Okay, so that proves this property. Okay. So anyway, as a corollary, pi upper star chow kx to chow k plus e pe is a split inclusion. Right, because I've constructed a splitting, namely S0. Well, or rather, this is pi lower star of zeta to the e cap blank. And we'll construct a map in the other direction. Okay, let me work out a lemma which I need for calculation later. Lemma E vector bundle of rank E plus 1 on x and L a line bundle. Then, if I take one of the Segre classes of E twisted by this line bundle, it's another vector bundle. This is equal to sum I equals 0 to p minus 1 raised to p minus I, E plus p choose E plus I, SIE C1 L raised to p minus I. So SP of the twist is a linear combination of SI's, I less than or equal to p, times powers of the Chern class of the line bundle with some suitable coefficients. That's the formula. Okay? So they both are operators of the same type. I hope it's clear, right? SI lowers the dimension by I, this lowers the dimension by p minus y, the product of them lowers the dimension by p. So every term is of that type. And it's an identity between some calculation. SP of, so the point is that you take the projective bundle or the projective bundle of E tensor L. These are canonically isomorphic, but the line bundles O1 are not exactly the same. There's a change. One, the formula, the relation is O P E tensor L of 1 is isomorphic to O P E of 1 tensor pi upper star L inverse. By the way, in my notes, here I have not put the exponent minus 1. But later in the calculation, the minus appears. As, I mean, there are minuses here, right? So, so the typo in the notes. It's an inverse. Let's just check, it's a routine calculation. Well, SP of E tensor L of some class beta is pi lower star of C1 OP E tensor L of 1 to the I, to the P cap beta. Cap pi upper star beta. But that's just the same as pi lower star of C1 OP E of 1 minus pi upper star C1L. to the P cap by sorry, P plus E, yeah. What do I want to do? P plus E. That's correct. Yeah, now then it's a routine thing. You just expanded binomial thing, write it out, use projection formula for these terms, and it comes out. Let me not waste time with it. Commutativity, associativity, all the formalism is used, of course. Then it is not difficult. But it's good to have the actual formula because I think I need to use it for some computation. So now, okay, maybe I briefly can start talking about Chern classes, which is what I really want to do. At least it's going in the direction of Grothendieck, Riemann, Roch, right? The statement uses Chern classes. I should somewhere Chern classes should come in. C1 is there. At least now I can get to the higher CI. So let E. Huh? Okay. I'm going fast in any case, yeah. But, right. So, the standard thing is to look at the formal series STE okay. And now you just try to define the Chern classes via the Chern series. I'm trying to define some classes by writing a formal expression, and the identity I want is STE times CTE equals 1. Now, if one has any doubts about the formal things, the thing is you can rewrite that as a bunch of formulae that C0 of E equals 1 and CPE is equal to C1E is of course minus S1E, and in general CPE is minus S1E CP minus 1E minus S2E CP minus 2E minus SP. So if one is at all uncomfortable with this, the formal aspects here, you can take this as an inductive definition of CP. Everything on the right side is defined inductive. Okay, so then the theorem is that these Chern classes have the properties that we expect. Let me write down the statement. And usual formula which follow from the other things, and then let me say C and D are projective bundle, proper push forward, and this one is flat pull back. Write the obvious statements, we can formulate them in They follow immediately from the other ones. But then there are some less obvious things. This is usually called Whitney sum formula in some circles. The usual formula. In other words, Ct E is equal to Ct E prime times Ct E double prime. Then let me write two other natural properties. X integral E in pick X a line bundle E isomorphic to OXD for some Cartier divisor D, then C1E cap X is just the class of D in Chow. Right, this is part of the business. I'm just saying the sign is now plus. And the last thing, if fy to x morphism of non-singular varieties E locally free on X, then Ci of f upper star E is f upper star Ci, where f upper star is the map constructed on Chow rings. This is not something obvious. I'm just saying if X happens, X and Y are both non-singular, there is already a theory of Chow rings which has been constructed. It's contravariant for mass. Its vector bundle also can be pulled back. And the Chern class of the pullback vector bundle is the pullback of the Chern class. This is another property. I'm just asserting it's correct. Now, how does one prove these things? Some of them are obvious, but some use the so-called splitting principle. Great. Let me just state it and then not give much detail of the proof. I've written something down here, but I'll try to see whether I want to do something with it or not. But yeah, probably nothing so different in what I'm doing. So let's see. Finite number of vector bundles on a scheme X of R type. There exists equidimensional flat and proper fy to x such that f upper star in the Chow groups of X to the Chow groups of Y, which exist because of the flatness, are injective. And each f upper star EI has a filtration such that the graded quotients Fi mod Fi plus 1 isomorphic to Li Fj mod Fj plus 1 is isomorphic to Lij in P. It's filtered by line bundles. So if I have finitely many vector bundles, I can find a map which is equidimensional, flat, proper even, and such that the induced pullback map is injected on Chow groups in every degree, and the vector bundles pulled back are each filtered by line bundles. So then under these conditions, so this has been apparently proved, so people should tell me if you want me to run through the proof again, I can do it next time, but if you feel it's routine, we skip it. Then the claim is, this implies, claim, under these conditions, if I have E on X, and I apply splitting, I construct a splitting map Fy to X for E, and the grade of F upper star E is the direct sum of Li, then the claim is that Ct of F upper star E is the product of 1 plus we formulate it like this. The churn classes of the pullback of E as well as the first churn classes of the different line bundles operate on the graded Chow group of Y. So when I write a formal series, I can think of it as something living in the ring, the endomorphism ring of Chow group of Y, and then take formal power series ring over that ring. So in that sense, these are equal. This again probably has been done by Amit, I suppose, but I want to go through it next time because it's got some conceptual points I want to emphasize. Okay. So, but I'm going to assume the splitting principle itself, but the way the identity is proved, there's a certain style of proving the identity which I think parallels in other theories and other things, and it's good to understand that. Amit might have in fact done it the same way, I don't care. I'm going to do it next time. Okay. So, but this then, if everyone is happy with it, I'm going to skip the proof of this. My notes do contain comments, but thank you.